You might notice a very distinct and almost distorted sound in the background soundtrack. I will talk more about that and other features of this sculpture later, but if you already want to know exactly what you're listening to, you can use the chapters below and jump straight to the end, where there will be a little showcase of the finished project. You can also choose to stay here with me and I'll give you a walkthrough of the entire process as best as I can. While I'm editing this video, I realized that not everything makes sense in a chronological order, so I've decided to group more suitable clips together, although they do not necessarily correlate to the order of operations. Before we begin, I should mention that all of the music in this video is produced by the sculpture and were recorded either during the breadboarding stage or from the direct output of the finished work. All good projects start with an even better trip to the basement. That's not entirely true, of course, as you still need to make the plans and drawings first, but for the sake of the narrative in this video, let's say that is not the case and skip directly to the rough preparation of the materials I will use. So while that is going on in the background, I'm going to take the opportunity to talk a little bit about the goal of this project. The initial idea or spark of inspiration was to make an electromagnetic listening device that would pick up signals from phones or other apparatus in the vicinity and vary in strength and character as people entered and exited its radius. That signal could then be used either in its raw form or as a means to modulate the behavior of any other circuitry in the sculpture. I attempted a few different approaches to FFT analysis in order to have the various frequency bands in the signal control separate functions elsewhere in the circuit, but in all cases I found the electromagnetic radiation of my own circuit to drown out the one of the nearby devices. Since I knew that this issue would only worsen when I inevitably would have to add a speaker, the obvious solution was to embrace it and look inwards rather than outwards for useful signals. I ended up wrapping a copper coil around my template speaker enclosure and fed its output in with the rest of the audio, which is programmed on a daisy seed and makes up for the bulk of the composition. This worked fairly well, but didn't sit quite right with the rest of the mix, so I added a bit of amplitude modulation to make it sound more 8-bit-ish, if you like. And that is, in the broadest sense, the story behind the audio of this sculpture. If you haven't yet seen the sculpture in action, what I'm about to say probably won't make much sense, but the title of this piece, Louver Counterfort, is essentially born out of the role the acrylic glass plays in this project, as it acts both as a manipulator of light and as a support for the semi-cantilevered speaker enclosure. When designing the lights for my works, I generally follow a couple of guidelines. First, that the light should represent an element in the music, and second, that the light should extend past its function as simply a light, meaning that it should also create movement in the object it inhabits. Ironically, I only filmed the routing of the black acrylic baseplate, but you'll understand when you see everything at the end of the video. Since we basically skimmed through the most basic handling of the materials in the beginning of the video, I'll go more into the details of the CNC process. I'm using two types of acrylic in this project. The black acrylic is 8mm extruded and the clear acrylic is 4mm cast. I made a minor mistake while 3D modeling by not taking into account the slight variation in thickness that is characteristic of cast acrylic, so if you're doing something similar in the future, keep that in mind, I guess. My go-to for routing acrylic is an 1/8 single flute bit with a 1mm depth of cut and a finishing pass for each of those cuts with an overlap of about 20% of the diameter of the bit. I'm fixating the workpiece with double-sided tape, so I usually measure the thickness of the acrylic quite meticulously and make the appropriate adjustments in my CAM software to prevent the bit from digging too deep into the glue and gumming up the bit and subsequently the edges of the material. If you have watched any of my previous videos, you already know that I'm a big proponent of this scaffolding system I'm about to show you, which essentially uses perf board and pin headers as guides or receptacles for the straightened tinned copper wires. The thicker of the two functions as a solid framework for the electronics to be mounted to and is connected to ground, while the thinner wires run in parallel with the scaffolding and carries various signals either within the module itself or to the rest of the ecosystem. Each one of these scaffolding modules usually contain electronics that are responsible for a certain type of task, such as oscillators, amplifiers and filters, but since this to a large extent is a digital project, I have one module that houses digital electronics and another one that holds buffers and inverting amplifiers for gain staging within the circuit. The grounds of these two modules are connected in a so-called star shape at the power input to prevent digital noise from seeping into the analog section, and it is particularly important to be diligent with the ground paths when using the daisy seed, as it has a certain notoriety for being noisy in the higher frequency range, and it is not helped by my decision to use a TC926 CPA charge pump to convert a positive power rail into a negative one, which conveniently is also very noisy. Speaking of the power rails, this sculpture is using a slightly strange configuration, as it is supplied by 15 volts and is, as mentioned, using a charge pump to provide almost -15 at the negative rail, so there is a slight imbalance there. Additionally, I'm using a VR10S05 switching regulator to provide 5 volts to the digital electronics. The reason why I'm using a 15 volt supply instead of, for example, a 12 volt supply is simply to provide a little bit more headroom for the TPA3110D2 Class D audio amplifier I'm using. The entire schematic is available on my Patreon page for those of you who are interested in those sorts of things. Link in description, of course. And while we still are in this chapter of power and scaffolding, you might have noticed the connector receptacles on some of the perf boards I've been soldering so far in this video. If you thought I was a freeform purist, you are wrong. Old-school wire routing can look beautiful. Just have a look at Rafe Greenacre's timepieces. I'll leave a couple of links in the description for that. Anyway, those connectors are Amp Modu Mod 2, which nearly fills all my requirements of a connector, which is that it should be easy to crimp and that it should be possible to correct insertion errors while also being easy to plug in and out of its socket. And the latter is where this particular connector fails. Regardless, in what could potentially be seen as a shallow attempt to cover up the discrepancy between the rigid and organized structure of the scaffolding system and the organic style of wiring, I added a light pipe to be zip-tied together with the rest of the cables so as to counterbalance the rectilinear approach of both the acrylic glass louvers and the electronic scaffolding. I am using 2 microcontrollers in this project, which might sound strange, and it is. It basically boils down to 2 things. First, that I'm an absolute fraud when it comes to programming, and secondly, that the daisy seed has some specific, inexplicable routines that are tied to the audio end of business somewhere under the hood, which are incompatible with certain Arduino libraries. At least that's what I, a peasant, have been able to gather from experience so far. Besides the Daisy Seed, which of course is responsible for the audio processing, I'm also using an Atmega 328 to control the TLC 5940 LED driver, which again controls the lights. To synchronize the two chips, I'm essentially sending audio sequencer information from the Daisy to the Atmega, so there's one pin that changes its state every time the sequencer is triggered within the Daisy, and another pin that changes state when the sequencer is at its end, so it really is just a resettable step counter. On the audio side, these sequencers are the bread and butter of the generative composition. There are two main synthesizer voices with two sequencers each, one for melody and one for rhythm, and on top of that there are two auxiliary voices that under certain conditions extend the harmonic range of any of the main voices. So for example, one of the two main voices is a fast and rhythmical sequence which at random moments can trigger its designated auxiliary voice to add a long note that sits either one step or a third above or below its main voice counterpart, while the slower and more melodic main voice has a similar auxiliary voice that operates an octave or two below and thus creates the bass notes. The other generative aspects of the music are typically conditional and include minor changes in timbre, pulse width, vibrato and scale changes, but most importantly, random elements in both the melodic and rhythmic sequencer arrays are frequently changed, and that's really what drives the music forward. The way this works is that the amount of times the rhythmical sequencer has run its course is being counted and stored in a variable, and when it has reached a certain number, say 4, there's a chance that any of these minor changes could happen. So for instance, after 4 rounds of a specific rhythm, a random number decides which element in the rhythmical or melodic array should be changed, and which value it should be replaced by. The same goes for the note range as well as the filter, so if by default the resonance value randomly interpolates between 0.4 and 0.8, either of these two values could then be changed to something higher or lower, resulting in an increase or decrease of the range that the resonance can operate within. While the digital section is mounted directly to the speaker enclosure, the analog section sits beneath it and is directly connected to the power and amplifier board at the left-hand side of the sculpture. As I mentioned earlier in the video, there isn't much analog to speak of really, as it's just a handful of op-amps that are used to either increase or decrease the gain of the signals that pass through them. So, for example, the copper coil is amplified by a factor of 510 before it's biased and voltage clamped, and then in another op-amp its signal strength is reduced further to conform with the max input voltage of the Daisy Seed. There are also a couple of buffers for the line outs, as well as some modest high and low pass filtering of the signal that goes to the audio amplifier. A major element in this sculpture is the speaker enclosure, and it is 3D printed. I'm not a big fan of what FDM 3D printed objects look like, and probably never will, but I did try out this black matte PETG filament, which, if you apply the appropriate amount of squint, looks okay from most angles. There are also other 3D printed objects in the sculpture, but often in less conspicuous areas, such as the base plate for the acrylic louvers. While 3D printers are fabulous tools, the strategy I found that works best when using them is to incorporate some other type of material to avoid big flat and blank spaces and replace them with what in my case often ends up being acrylic glass. The other benefit to this is that by combining these two materials, that is the 3D printed part and the acrylic glass, you need some way to join them, for instance with bolts, which adds a bit of intricacy to the part, and you end up with a much more organic or even industrial looking object. There's also the weight factor, which can make anything feel more luxurious, for lack of a better word. So we are currently in the final assembly stage, and as you watch me desperately try to spin this coil, I just wanted to mention that you will see examples of what I just talked about throughout this chapter, and hopefully it will make more sense. I did not count the amount of turns I did when wrapping this coil, and I have no idea what its inductance is. The most important factor is that it's able to pick up electromagnetic signals, which it does. As I mentioned earlier, the coil is wrapped around the enclosure approximately where the speaker driver is located in order to create an electromagnetic feedback of sorts, where the coil picks up its own signal for it to be re-amplified along with the rest of the audio. The speaker I'm using is a Dayton ND65 with a matching passive radiator on the rear of the enclosure. The passive radiator might be slightly superfluous in such a decent sized enclosure, but it should ensure that the low end is appropriately responsive. To prevent the vibration of the speaker from manifesting itself in the wire scaffolding and thus adding unwanted noise, I'm using vibro isolators, which are essentially threaded rubber spacers. To these I'm attaching an acrylic glass plate which will hold the digital section of this work, which later will be connected to the rest of the sculpture through a combination of flexible wires and straight copper wire. I've recently been obsessing over the various standards of mechanical hardware, so for the handful of you who are interested in this, the nuts I'm using to fasten parts that may be subject to vibration or otherwise are under some form of load are of the DIN 985 standard of prevailing torque nuts. Most of the LEDs in this sculpture are, as mentioned, driven by the TLC 5940 and are squeezed and glued into drilled holes in the undercarriage of the louvers. Here I have 3 rows consisting of 8 LEDs each, where 2 of these rows are white and the remaining row is orange. The white ones represent the fast, rhythmical voice, while the orange represent the slow and melodic one, and the idea was that these 2 colors would blend as the voices ran through their respective sequencers. As for the UI, you have 3 potentiometers. One is for the speaker volume, while the other 2 control the volume and the amount of rhythmical gating applied to the electromagnetic signal. Because the coil is dependent on the activity of the speaker driver, the overall volume knob is also in some capacity responsible for the amount of electromagnetic feedback in the signal, which essentially means that you can't turn the volume all the way down and still expect to hear the coil in the audio from the direct outputs at the back. I think I've said all there is to say about this sculpture, really. I'll let you watch the rest of the video in peace, but if you have any questions, I'll try to answer them in the comments.